This video is about torque, and let's start with a picture of a door. We're looking down on the door from the top, and in order to open the door, you would push on it with a force, and that would turn the door around its pivot, or its axle over here, the hinges. So clearly the force is important in turning the door, but also where you apply that force is critical. So we need to take into account the distance between the hinge and where the force is applied. That we call R, the force we call F. And it's the product of those that creates torque. Torque is the rotational equivalent of force. If I push on an object with a force, it moves in a line. If I push on an object that has a hinge or a pivot point, if I push on it with a force at a certain distance, then that creates a torque which causes it to turn. So everything we've learned about forces and kinematics in the linear space translates to the rotational. And so we can see that if I applied the same force over here, it would not turn the door as much. And so we all know from experience that if we want to open the door as easily as possible, we put the force at the end of the door where it's most effective. So what we're looking at is really the force that's perpendicular to the door, applying at a point a distance r from the axis. So we're going to define torque as the perpendicular force times the distance from the axis. Force is in a unit of newtons, the distance is in a unit of meters, so the units for torque are Newton meters. This is a little confusing because Newton's force times distance is also work. So we want to kind of keep in mind that this force times this distance is different than work. Now, in a more general sense, the force may not be applied to the door at a perpendicular angle. Let's say I'm going to pull on the door with a force like that. If I break it down into its components, some of the force pulls the door outward. Let's call that F parallel. Some of the force makes the door rotate. Let's call that F perpendicular. If I pull on the end of the door with F parallel, that doesn't turn the door in any way, shape, or form. It just pulls on the door. On the other hand, if I push or pull with a force that's perpendicular, then I create a torque. So let's look at the geometry of this. If this is my angle theta, I now have a right triangle here, and I'm trying to find the size of the perpendicular component. Well, the sine of theta equals the opposite, F perpendicular, over the hypotenuse, F. So therefore, F perpendicular equals the sine theta times F. So in this situation, we can calculate the perpendicular force by using the sine. I'm very reluctant to put this information, the sine or the cosine, into the definition of torque because each situation is different, the angle is different. So I'd like you to remember that torque is the force that's perpendicular to the object, and r is the distance from the hinge. In this class we won't use it, but there's also another form that, if you look at the geometry of it, this is the same as the force times the component of r that is perpendicular. We won't use this in our class, but it's something that might be useful to know.